In multi-step equations, there's a few additional things we need to consider, and I have a few examples here. So just looking through them. In the first case, we have more than one term on one side of the equation. In the second case, we have a bunch of terms on both sides, and then even multiple variables. I see an x, 2x, 2x. Well, the same variable, but multiple cases of that variable. And then these other three have maybe parentheses or some additional operations that are happening. So the first thing we can ask is, what order should we operate in? Like, what should we do first, second, and last, and all of that? And then the second question that comes up is, what can we combine together? And that's the issue of like terms. So let's go through these and see how these issues come up. So in the first case, number 5, we have two terms on the right side. I have a variable on the left side. The goal for all of these is the same as a one-step equation. I just want to get my variable by itself just equal to something at the end of the story. So in general, if I see some parentheses like this, there's this double negative, that's usually the first thing that I'll take care of. So minus a negative, we can turn that into plus positive. So let's at least clean up that right side. And the left side the same. Minus 9x equals now 19 plus 17. So it probably feels pretty natural to combine these together, and this is what we'll call like terms, things that we can combine, so we can add two numbers together. The other thing that we can combine is two expressions with x that we can combine together, and those will be our two main cases so far. Okay, on the right side, 19 plus 17, that will combine to a 36. And then now we've arrived at a one-step equation, so we've simplified down to what we've seen before. So let's divide both sides by negative 9. Negative 9. So it cancels on the left side. 36 divided by 9. And we're dividing by a negative, so positive divided by a negative will give us a negative. And then dividing the 36 by 9 will get a 4, so negative 4. We can go back in and plug it in if we need to check it. Okay, so this is the idea of like terms, things that we can combine together. And so obviously two numbers that don't have a variable are like terms. On number 13, we have multiple x's on both sides of the equation. So we can ask, like, which side should we start on? And the answer is it's kind of up to you. We have some freedom in solving multi-step equations as long as we follow the rules of algebra. That's the only catch. So we can work on simplifying, say, the left side first, and then work on the right side and kind of go back and forth if we want to. So let's start with the left side. I'm looking for things I can combine. So I see this x and the 2x. I can't combine with the 17 because it doesn't have an x, but there's one x here, there's two x's here, so together that will make 3. We can combine those together. So let's simplify this to 3x. We still have this plus 17. And we can work on the right side too. So on the right side we have the negative 2x, and then this minus 19 and minus 24. So in this case, the negative 19 and the negative 24 are like terms. We can combine those together. The minus 2x will have to just leave there. So negative 19 minus 24, let's see, that will combine to negative 43. So I'm going to just leave this minus 2x there. And then these two combine together to minus 43. Okay, now we can pick up from here. So now we have kind of a similar situation on either side. One term with an x, and then one term without an x. So let's keep in mind what the goal is. The goal is eventually just to get x by itself equal to some number. So we want to eventually collect all of our x's on one side. And we can use the left side or the right side. Probably used to moving things over to the left side, but either side will be fine. So let's just work on collecting all of our x's. I have this minus 2x here. Let's move it over to the left side. So I can imagine adding 2x or moving it over with the opposite operation. So 3x plus 2x will get 5 on the left side, and we still have this plus 17. So we'll bring that down. And then I have this minus 43 on the right side. So now we're looking maybe more like our first one. And we're still trying to get this x on its own, so let's take this 17 and move it over to the right side. So it's positive, so we'll subtract it on the right side. So I have minus 43 minus 17. That will give me a negative 60. So we're subtracting from a negative. I'll add those together. The result is more negative. So 5x equals negative 60. So now we're left with a one-step equation. So let's divide both sides by 5. Cancels on the left side. We get x equals negative 60 divided by 5. That will give us a negative 12. So we can work a little on each side, combine like terms with the ultimate goal of getting our variable on one side equal to a single number. In number 15, we have a little bit of both things happening here. So let's deal with the double negative, and then we have this 8 underneath our x. So just like in number 5, we can clear out these parentheses by turning that into plus positive. So negative 30 plus 22 equals x over 8. And then now we have some like terms on the left side. So let's combine these two. Negative 30 plus 22, I can view that as like 22 minus 30. The result should be negative. Looks like a negative 8. So it should be negative 8 equals x over 8. Let's move this over here. So I have x being divided by 8. Let's move it to the other side by multiplying both sides by 8, or just moving it over with the opposite operation. So negative 8 times positive 8 will give us a negative 64. Add this over here. Sorry to squeeze this in. It's almost like a mirror image of number 5, except we had a number being divided underneath our variable. We can combine like terms, deal with the double negative. In 16 and 20, these are examples of equations that have parentheses with little expressions inside of the parentheses. So those are the things that I'll work on dealing with first. This is kind of related to order of operations, where I would first try to deal with the parentheses before anything else. So if I see something like this, some parentheses with a number in front, the way to clear it out is to distribute it through to each term inside. So it's going to go in and multiply. It'll multiply with each term. So I'll view that. Maybe we'll write it out first. Oh, and we do have some like terms on the left side. Let me leave this for now. Let's just do one step at a time. So these will both multiply. 2 times x will give me 2x. Those will stick together. And then 2 times negative 9 is negative 18. So I'll just go one by one and multiply those numbers. So that's called the distributive property. It distributes to each one. Now we're kind of like where we were in a previous question. On the left side, we have two like terms we can combine. 18 minus 12. That looks like a positive 6. So 6 equals 2x minus 18. We can solve it on the right side. Let's add the 18 over. Plus 18. 18 plus 6. Looks like 24. So 24 equals 2x. And then we'll divide both sides by 2. So just little moves. Simplify it a little bit piece by piece, trying to clear things up, move things to the other side. 24 divided by 2 is a positive 12. So I'll say x equals 12. And you don't necessarily have to know exactly what all the steps will be as you go through. You can kind of figure it out as you go. As long as you just make a good right move, you can pick a good side to work on. I'll always recommend clearing the parentheses first. But the answer can kind of reveal itself as you go along. We don't necessarily have to see the whole path. So like on number 20, we have parentheses on the left side, parentheses on the right side. We can choose either side to work on, or even distribute them both in one step if we want to try to do them 2 for 1. So the 4 will go in and multiply with both terms. 4 times 4 is 16. 4 times w is 4w. If you're ever multiplying a number times a variable, they just stick together. Or if this already had a number, then those numbers would multiply. If this was like 2w, I would get a 8w there. And then let's send the 3 through. So that'll give me 3 times 3 is 9. 3 times w is 3w. So 9 plus 3w. Okay, so we've cleared the parentheses. Now let's choose a side to move over to. Let's keep the w's on the left side. So let's subtract 3w from both sides, and I can just imagine it subtracting it from that 4w. Minus 3w. So I get 16. 4 minus 3 is 1, so I'll just have 1w left. 16 plus w equals 9. That one was moved over. Now let's just subtract the 16. So 9 minus 16 should give us a negative 7. We're subtracting a larger number. So w equals negative 7. So we're still using all the same kind of moves from one-step equations, adding something or subtracting, multiplying, or dividing on both sides. Now we just need to do this maybe a few more times in each equation. And you can imagine how we can keep expanding this and making it more complicated. So word problems can be tricky because we have to take the paragraph of words and convert it into some kind of mathematical expression, and that can be the tricky part. So there's a few questions just to practice that process. In number 11, we're asked to convert this to some expression. The product of negative 12 and a number increased by 5. So product, that means multiplication. So I'm going to go through and just kind of annotate this, and I'd recommend doing something similar. Just like make little notes, maybe even just in your head. So the product of negative 12 and a number. So just something unknown. If you see some general phrase like that, you can make that our variable. Let me use my x for this, and let's turn that into like a dot multiplication symbol. Increased by 5. Increased means we should be doing some addition. We're going to add to 5. So let's try to convert that into an expression. Product of negative 12 and a number. So multiplying negative 12 in x, the product of negative 12 and some number that we can maybe later define, increased by 5 plus 5. So a little conversion from the English language to the mathematical language. And this one is more of an equation. 7 is 3 more than a number. Something is 3 more than something else. So 7, or number 7, is in a sentence usually means that that'll be an equal sign. Something is equal to something else or has some relationship. So that usually denotes some kind of is equal to. 7 is equal to 3 more than a number. There's that a number again. That's a good placeholder for our variable. So we can say 7 is 3 more than a number. It feels kind of backwards. We can say like x plus 3. 3 more than some number. 3 plus x would have worked out, but I feel a little more comfortable writing it in this way. Okay, just some practice in this translation. Let's apply it to an actual word problem. And I've shortened this a little bit just for the board. But it's about 2 species. It says species A, some species of bird, can fly 5 times as fast as species B. If their total speeds are 228 miles per hour, find their separate speeds. So what is it asking for? That's the first thing that I'll look for. Like, what is the ultimate thing I'm trying to solve for? I need to find the speeds of these 2 species. So let's just call that A and B. A is like the speed of species A. This feels a little redundant. I'm just kind of defining some terms that I'll use. B, we'll say, is the speed of species B. So I'm just kind of making notes as I read through this question and starting to add some labels. So our ultimate goal is to build some equations to solve out of this word problem. And usually for these kind, when we're at this stage, it'll usually involve two equations, and we can use one variable in our set of equations. So let's try to define what that will be. And we see some relationships stated in this problem. Species A can fly 5 times as fast as species B. So some relationship, they're relating A to B. A is 5 times faster than B. And their total speeds are 228 miles per hour. The total statement, which you try to search for that in a word problem, you'll maybe see some kind of total thing. That's an easy one to make an equation out of. Their total speeds are 228 miles per hour. Whatever A is plus whatever B is, if we add those together, the total is 228. Okay, we can't really solve anything for this yet, but we at least have some kind of equation to start to think about. And then we have this other statement: species A can fly 5 times as fast as species B. So we need to label something as X. And since we're relating A to B, let's make whatever species B's speed, whatever that is, let's make that X. We'll just say that's equal to X. And A is 5 times as fast as B. So let's say A equals 5 times X. So two little statements. We're defining these speeds in terms of some variable. So you'll see different variations of this type of problem. Maybe something is just like a few more units more, like 3 more than something, or 5 times as, in this case, I multiplied. But try to come up with some kind of expression in terms of your variable. That's what it's trying to get you to do here. So we have these two expressions for A and B. Let's plug them into our total equation. This is usually the one that we'll be able to solve for. So let's replace A with 5x. That's 5 times as fast as the speed of B. And B, that speed we said was just x. So 5x plus x. That total is still 228. Well, now we have a little equation that we can solve. We can solve for x here. These are two like terms we can combine. So 5x plus 1x is 6x equals 228. And then let's divide both sides by 6. So 228 divided by 6 gives me a positive 38. It's tempting to stop right here because we've solved an equation. I see x equals something, used to just kind of ending it there. But since we're in the context of a word problem, we need to reinterpret and actually answer what they were asking for. Because from the start, they were looking for both the speed of A and B. If I just say x equals 38, there's little context here. And we can add our units back in. This was miles per hour. But what does x stand for? We can turn back to how I've defined things. This is why I like to write it out at the start so I can come back and reference it. I said x was the speed of species B. So species B is 38 miles per hour. And species A is 5 times this number x, and x is 38. So species A should be 5 times 38. And say 5x is 5 times 38. Let's see what that gives us. I get 190. So that will be our speed of species A, 5 times the speed of species B. 190 miles per hour. So I go through a few kind of set stages when I'm trying to make it through a word problem. The first is just to read through the whole thing and try to get some sense of what's happening. If it involves some kind of geometric shape, it's useful to draw out a picture, although this is birds flying, so maybe that would be less helpful for us. So I first read through. If I can draw a picture, I'll do that. And then I start to just go through and maybe underline or annotate things that look interesting to me. Maybe first determine what they're asking for. Look for like some kind of total statement, total speeds are 228. We get this like 5 times as fast as species B. So little things that we can build relationships out of. I'll define some variables, in this case one variable, set up our equation and see what I can plug in. The ultimate goal is to get to this kind of stage where you have a single equation with just one variable that we can solve from there. So it might take a few times and some time to develop your own process. And I know the textbook I think they have a good list of steps that you can follow as well. Okay, so give these a try and let me know if you need help. So when we're solving equations with fractions, the goal is still the same. We just want to get our variable on one side equal to something on the other side. We just have to be careful, and we're forced to obey the many rules of fractions. And as you may know, the rules change depending on what operation we're using, either adding, subtracting, or multiplying or dividing. So let's see how those show up as we work through these examples. In number 27, I want to solve for y. Let's move the 17/23 over to the right side. It's being subtracted, so let's add it to the right side. Do that as moving it over, plus 17/23. So I have 17/23, and I'm basically subtracting 11/23. It makes pretty good sense that I'll have 6/23 left over, 17 minus 11. The denominator is like the units that we're working with. So if we're adding or subtracting two fractions, we have to have the same denominator in order to perform the operation. That's the first condition, and we're lucky enough to already have that as the case here. So I'll keep the same denominator, 23, and then perform the operation on the numerator. This was technically negative 11 plus 17, or 17 minus 11, leaving us with a positive 6. So for adding or subtracting two fractions that already have the same denominator, just keep that denominator and do the operation. But what if they're different? So that's our case for number 28. I have x minus 1 over 40 equal to 19 over 20. Let's still at least move that over. That'll be our good first step, plus 1/40th. So let me just write it down here. X equals 19/20 plus 1/40. It's like they have two different units. We can't quite combine them together yet. So the goal is to get like our first case where we have the same denominator. And luckily with fractions, they're pretty easy to change. We can always multiply some number into a fraction as long as we do it on the top and the bottom. In that case, we're just scaling the fraction. We're not changing it, just kind of expressing it in a different way. So one thing we can do is try to change one denominator into the other. That's usually the first thing that I'll look for. If they're not the same, I'll say, okay, looking at the smaller one, is there some number I can multiply here that will turn this number into the other denominator? In that case, yes, if we multiply 20 by 2, we'll get 40. So I want to do that to the left fraction, multiply by 2, but I need to do that on both the top and the bottom in order to scale it properly. So this will transform into 19 times 2, that is 38, divided by or over 40. So 38/40ths plus 1/40. Now they have the same units, the same denominator, so 38/40ths plus 1/40th is 39/40ths. Now I can just add the numerators. And the denominator stays the same. So that's usually the first thing that I'll look for if I'm needing to add or subtract two fractions with different denominators. Can I just multiply the smaller one times some number to get the bigger one? And I'll do that on the top and bottom. That won't always work out, but if that does, then it's an easy way to start to combine them. In number 30, a little bit different from the previous two, we really just need to get rid of that 9 that's multiplied by m. We want to divide it, but it's going to divide over into this fraction. So I just want to discuss what we can do to simplify this. So we're dividing by 9. There's two ways we can look at the right side. I have 1/5 kind of as one object being divided by 9. One way to view this is to view it as a division of two fractions. So I have, in a sense, 9 over 1. You can always put a whole number over 1. So I can write it out this way, like 1/5 divided by 9 over 1. When we're dividing two fractions, the way to divide is to, you may have heard the phrase keep, change, flip. Keep the first fraction, change it to multiplication, and then flip the second fraction. So flip the second fraction and then multiply. So this will be equal to 1/5 times 1 over 9. And when we're multiplying two fractions, you can just do the top times the top and the bottom times the bottom. So let me get this in here. 1 times 1 is 1, 5 times 9 is 45. And our variable was m. So that's viewing it as a division of two fractions. Just to show another slightly more straightforward point of view, if I'm dividing this 9 over, it's going to go in and multiply into the denominator of that fraction. You can view this division as like the 9 is going in and joining that 5, since from one perspective that 5 is already being divided here, so it's like going to go and join the right side underneath, and that 9 will go in and multiply with the 5. So 1 over 9 times 5, which is our 45. So we're being a little bit loose there. Technically, this is what's happening. We're doing like a division of two fractions, but you can view it as going in and multiplying into the denominator. It can be a little bit of a shortcut. But when in doubt, you can always write it out. I like to write it out as like a linear division, something divided by something, division of two fractions, and that can help me see it a little bit more clearly. I'll just flip the second one and then multiply them together. Okay, in 32, we have some fraction times our variable equal to another fraction, so a little bit messy here. One way to clear a fraction is to multiply it by the reciprocal. The reciprocal is the flipped version of a fraction. Meaning I have 11 over 16 here. If I multiply by 16 over 11, it's going to cancel both of these at once. It's kind of like multiplying and dividing at the same time. And I'll do that on the right side. So multiply by 16 over 11. So we need to do that on both sides. So we're applying the multiplying property of addition. We can multiply any number we want to on both sides of the equation. So we just choose one carefully that cancels both the numerator and the denominator at the same time. And the shortcut is just to flip it. Use the upside down version. And then we just need to simplify this right side. Let me write this out here. We had negative 4 over 48, now times 16 over 11. Okay, so we can multiply this out. We're multiplying two fractions. We can do top times the top, bottom times the bottom. But before we even do that, and this is useful if maybe not working with the calculator, we can try to simplify things so we don't get too large of a number. Like, I'm curious, does 16 go into 48? Does this simplify in some way? I can test that out. 48 divided by 16 gives me a 3, so I can say 16 goes into 48 3 times. And I could check this too. Does 4 go into 11? In that case, no, so we'll have to leave that as it is. So let's just simplify this. We're technically left with a 1 up here. So negative 4 times 1 is negative 4, and then 3 times 11 is 33. Negative 4 over 33. We can go in and check it if we need to. So we did this reciprocal multiplication to cancel. And then here we did a little bit of careful cancellation before multiplying. We would get the same result if we did the full multiplication and then reduce the fraction from there. So we will arrive at the same result. In number 34, try to section this off a little bit. We have 3 different fractions. We can try to get a common denominator and combine them all together one by one. But one method is to try to clear all of the fractions in one equation all at once. So we can try to find, is there something we can multiply all 3 of these terms by that will cancel with the denominator? Like we did some canceling here. We want everything to cancel cleanly. What we want is called the least common multiple. You can see that abbreviated as LCM between these 3 numbers. And that can take some time and maybe a little bit of guessing and checking to find. But if you notice with 8, 5, and 40, 8 times 5 gives us 40. So that means we can, if 40 is divisible by 5, 40 is divisible by 8. And then 40 over 40 would cancel as well. So we can multiply this, in a sense, this entire equation by 40. Let's imagine it like distributing to every term. And I'll write it like this. So 40 times 9 over 8 minus 40 times k over 5 equals 40 times 1 over 40. And it kind of looks like we're making this a lot messier, but let's see how this will clean things up for us. If I imagine each of these 40s as being over 1, 40 over 1, 40 over 1, 40 over 1, we can do a similar cancellation here. Like 8 goes into 40 5 times. You can say 8 goes into itself 1 time and into 40 5 times. 5 goes into 40 8 times. 5 goes into itself once and into 40 8 times. Notice we're just getting ones all on the bottom here. And then 40 cancels with itself. So let's see what we're left with. 5 over 1 times 9 over 1, that's just 5 times 9, minus 8 over 1 times k over 5, or 8 times k, equals 1 over 1 times 1 over 1. This just canceled out to be a positive 1. So we multiplied by the least common multiple to cancel all of the fractions. It can be a little bit tricky to find the right number that will do that, but once you do, it cleans everything up quite nicely. 9 times 5 is 45, so 45 minus 8k equals 1. Now let's just solve this equation. Subtract the 45 over. I'm left with this minus 8k on the left side, and then 1 minus 45 will be negative 44. And then let's divide both sides by negative 8. So we'll cancel on the left side. We just have to simplify this fraction. I'm left with the k. I have a negative divided by a negative, so that will become positive. Those will cancel. And then 44 isn't directly divisible by 8, but they're both divisible by 4. I can divide 44 by 4, that will give me 11, and 8 by 4 will give me a 2, so 11 halves. So lots of trickiness with the fractions. This one involved many of the rules, but this is one way to clear out all the fractions in an equation. If you can find the right number where each of the denominators will divide into that number. And it can be one of your denominators, and that was our case here. We can use 40 itself, because you can always cancel 40 with itself. So it's a tricky way to clear things out. And then 39, it just wants us to combine these two. At first glance, they appear to be not like terms, and in a sense they aren't, because x and 6 are not like terms, but we can at least combine this into a single fraction. Let's view this 6 as a 6 over 1. So x over 2 plus 6 over 1. We said previously if we're trying to add or subtract two fractions together, we need a common denominator. So I'm looking, can I turn the smaller one into the larger one? 1 is pretty nice. We can multiply 1 by anything. So let's multiply this by 2 on the top and bottom. So I have x over 2 plus 6 times 2 is 12 over 1 times 2 is 2. So now I have the common units, common denominator. So the way to combine this, we still won't combine the x and the 12, but we can at least write this in a single fraction with a common denominator, just as x plus 12 up top. And there just may be some situations where it will be beneficial to do this, so I'm kind of practicing that skill. It may not yet be obvious how helpful this will be, but we can treat any single number, like any whole number, as a fraction, as long as we've just put a 1 underneath, and then we can change that 1 into any denominator and combine it into a single fraction. But again, since x and 6, this ended up being a 12, since x and 12 aren't like terms, we'll just leave it like that, x plus 12 up top. All right, so many rules of fractions. Just have to be careful as we go through.